Wet runway takeoff performance. Takeoff performance on a wet runway presents a unique challenge to transport airplane pilots. In this program, we will review the certification history for accelerate stop distance and takeoff distance, the differences between wet runway and dry runway performance, and key points for performance planning for taking off from a wet runway. A requirement of transport airplane performance planning is determining that the takeoff can be safely conducted on the length of runway declared usable for takeoff. The certification rules for these airplanes prescribe 3 distances that must be considered: the accelerate stop distance, the takeoff distance, and the takeoff run. Of particular importance is accelerate stop distance, or the distance required to accelerate to a point in the takeoff, then in response to an event, take the first action to reject the takeoff at a speed no greater than v1 and to bring the airplane safely to a stop. Originally, the accelerate stop distance did not include consideration for events other than engine failure that could lead to a rejected takeoff. In 1978, the certification rules were amended to consider both engine failure and non-engine failure scenarios. Accelerate stop distance was revised to be the longer of the distance with one engine failing just prior to V1 or with all engines operating throughout the rejected takeoff. However, accelerate stop distance was still determined only for a dry runway. In response to the disproportionate number of rejected takeoff accidents on wet runways, the certification rules were again amended in 1998. Manufacturers are now required to provide wet runway accelerate stop distance and wet runway takeoff distance data in the airplane flight manual for all newly type certificated transport airplanes, and the operating limitations and rules require the use of this data when the runway is wet. Typically, the minimum field length required for takeoff in a 2-engine turbojet transport category airplane is based on the balanced field length concept, where the accelerate stop distance is equal to the 1-engine inoperative takeoff distance. The balanced field length can be obtained when, for a given takeoff weight, a V1 speed is selected such that these two distances are equal. When the runway is wet, the accelerate stop distance increases due to reduced friction during braking. The braking friction on a wet runway varies greatly with speed, while it is essentially constant with speed on a dry runway. At faster speeds, the wet runway braking friction is much lower than at slower speeds. The reduction in braking friction is partially offset by the stopping performance credit permitted for the use of thrust reversers on a wet runway if they are installed and operative. On a dry runway, the 1-engine inoperative takeoff distance ends when the airplane reaches a height of 35 feet above the runway. To reduce the V1 speed to both rebalance the probability of rejecting a takeoff on a wet runway versus continuing that takeoff and to reduce the speed at which braking would be attempted, the regulations allow us to consider that the wet 1-engine inoperative takeoff distance is complete when the airplane reaches 15 feet rather than 35 feet required for a dry runway. Reducing this screen height also reduces the 1-engine inoperative takeoff distance on a wet runway. The allowance for reverse thrust credit and the use of a 15-foot screen height help the engineers rebalance the takeoff field length required for takeoff on a wet runway through the use of a lower wet runway V1 speed. The ability to reduce V1 speed can be limited by VMCG speed and the lowest permissible V1 speed in relation to this ground minimum control speed. When V1 speed is limited by VMCG speed, the takeoff on a wet runway will be accelerate stop limited. Note that the all engines operating takeoff distance for a wet runway remains unchanged from that for a dry runway. The all engines operating takeoff distance screen height for a wet runway remains at 35 feet and still must include the 15% margin. In most cases, the maximum allowable takeoff weight on a wet runway will remain less than the allowable weight on a dry runway, even though the wet runway case includes credit for available reverse thrust and reduced screen height. However, there are exceptions. Rocky Mountain Regional Airport, better known by most as JEFCO, presents an interesting wet runway example for some turbojet airplane types. Runway 11 left, 29 right is the primary runway used by jet airplanes. Runway 29 right is 9,000 feet in length. The runway also has an upslope of 1.2%. A check of a takeoff analysis for one particular business jet type finds that the takeoff weight limit on a wet runway at 20 degrees Celsius appears to be 36,030 pounds. On a dry runway for this same airplane type, the maximum takeoff weight is 33,840 pounds, or almost 2,200 pounds lighter than the apparent weight limit previously calculated on a wet runway. At 33,840 pounds, the balanced field takeoff distance is precisely 9,000 feet, the length of runway 29 right. However, at this same weight, the balanced field takeoff distance on a wet runway is only 8,000 feet. The reduced screen height and credit for use of thrust reversers determining the wet runway takeoff performance can in some cases actually produce a situation where at a given takeoff weight, the wet takeoff performance appears to be better than the dry runway performance. This can lead to a situation where the wet runway analysis produces greater takeoff weights than the dry analysis, but the certification rules have an additional requirement to address this situation. These rules specify that the accelerate stop distance and the one engine in operative takeoff distance must be the greater of either the dry runway or wet runway distances. This requirement is reflected in the instructions furnished in most FAA-approved airplane flight manuals, where wet runway takeoff performance data is furnished. Users are advised to check the distances required or takeoff weight limits determined on a wet runway against those for a dry runway condition and to use the most restrictive distance or weight limit. In some instances, the airport analysis furnished will incorporate this dry check. However, users should verify this feature with their performance engineering services provider for their aircraft. While the scope of this discussion is focused on takeoff performance planning, pilots of transport category airplanes should also be familiar with the takeoff safety training aid. The goal of this aid is to reduce the frequency of rejected takeoff accidents through improved pilot knowledge and awareness of the factors affecting the successful outcome of the go, no-go decision. The Takeoff Safety Training Aid may be viewed at the FAA's Airline Operator Training website. In summary, when performing departure planning from a wet runway, pilots should have a general idea what the effects of this wet surface will have on accelerate stop distance and takeoff distance. Operators should ensure that the evaluation of the takeoff weight limit for both wet and dry conditions is performed, and that the most restrictive weight, the lighter weight, is used for takeoff and that a wet runway V1 speed is used. This is true whether manual computations are being performed by the pilots or vendor-provided takeoff computations are being utilized for departure planning.